Here's something that's a very important question you should always be asking yourself if you're going to talk about approximations. You remember we were talking about using Taylor polynomials to approximate our original function f. Here I wrote this incorrectly. This should be a minus sign. We can make precise this idea of an approximation by talking about the error, or in this case, it's given the name r sub n, the remainder, for the nth degree Taylor polynomial, or sometimes you would call this the nth degree Taylor remainder for the function f. That's just the original function f minus the nth degree Taylor polynomial. It's what you get if you add up all the terms in the Taylor series beyond the nth degree term. These are all the ones that you're skipping if you're just using t sub n to approximate the function f. If you're going to use the nth degree Taylor polynomial to approximate f, you have to have at least some idea how good an approximation it is. If you don't know how good the approximation is, it's not more useful than just saying 7 all the time as your approximation. So how close is t sub n of x to f of x? In other words, how small is this error or remainder term r sub n of x? Well, Taylor series are named after the mathematician Taylor, primarily because of Taylor's theorem, which tells how close the remainder is, or how small the remainder term is. It says the absolute value of this nth degree Taylor remainder is bounded by a simple expression like this. It's some constant m, which we'll talk about in a minute, over n plus 1 factorial times the absolute value of x minus a to the n plus first power here. Here, m is just some constant, which is an upper bound for the n plus first derivative. Make sure that that's the n plus first derivative of f, not the n plus first power of f. The n plus first derivative of f at some number c, where c is between a and x. In other words, you can choose for m the largest value of this n plus first derivative on this interval between a and x. And remember, we need the absolute value of this. So if the n plus first derivative is negative, we need the absolute value of that largest magnitude of the n plus first derivative. So if somehow you have an idea how big that n plus first derivative can be, you don't need to know exactly what it is, just an upper bound, some number which the n plus first derivative is not bigger than. Then you just divide by n plus 1 factorial and multiply by x minus a to the n plus 1. Remember here, a is the center of the Taylor series. So this shows you if you keep your x close to the center of the Taylor series, this quantity x minus a will be small. And if that's small and you raise it to a high power, if n is pretty big, it will become really small. Notice you're dividing here by n plus 1 factorial. If n is big, n plus 1 factorial gets large very quickly. So again, these things, if x is close to the center A and if n is big, make the nth degree Taylor remainder very small. What would make the Taylor remainder big is if x is far away from the center A. You saw in the pictures in the last video that if you use the nth degree Taylor polynomial to approximate a function, but you look at a value of x that's very far away from the center of the Taylor series, then your Taylor polynomial is probably not going to be a very good approximation, which means the error term, this remainder term, will be large. And that's shown here. If x minus a is large, then when you raise it to the n plus first power, that can be really large, and your remainder will in general be pretty large itself. You still have this n plus 1 factorial in the denominator, which can help keep things small, but you want to keep both small if you want the remainder to be really good. Now, the proof of this is beyond the scope of the course, but let's take a look at some examples of how this works. Let's look at this function, the cosine function, and we already saw before that the fourth degree Taylor polynomial is just 1 minus x squared over 2 factorial, which is just 2, plus x to the fourth over 4 factorial, and of course 4 factorial is 24 there. This is the fourth degree Taylor polynomial. If we want to know how close this fourth degree Taylor polynomial is to the cosine function, well, we have to ask, where are we interested? This is the Taylor polynomial centered at 0, and if I say move x all the way out to 1, say 1 unit away from the center of the Taylor series. How good an approximation is T4? Well, T4 of 1 is just what you get when you plug in 1 here. That's 1 minus, this would be a half, and then we add 1/24. That's exactly 13/24, which is approximately 0.5417. Here's a question: how close is that thing, 13/24, to the actual value of f at 1, which is just cosine of 1? That's some strange irrational number. Well, Taylor's theorem tells us that the error is what we call R4 of 1, the fourth degree Taylor remainder term at the value 1. And Taylor's theorem tells us that the absolute value of that error, of that fourth degree remainder term at 1, is at most m over 4 plus 1 factorial. That's 5 factorial. And remember, 5 factorial is 1 times 2 times 3 times 4 times 5, which you can multiply that together in your head. You'll see that's 120. And you have to multiply by x minus a. This is our x here. We're choosing to look at 1. And this is our a. The center of the series is 0. So that number is just 1 to the 5th power, which is just 1 here. Now, what do we use for m? M has to be an upper bound for the 5th derivative of f at x, or I'll say at c, where c is between 0 and 1. Well, for this function f, I won't even write it down. F of x is cosine x, f prime is minus sine x, f double prime is minus cosine x, f triple prime is sine x, f4, the fourth derivative, is back to cosine x, and f5 is minus sine x. All of these derivatives of f are either plus or minus sine or cosine of x, which means their absolute value is never bigger than 1. I don't know exactly what the absolute value of sine of 1 is, but I know it's not bigger than 1. So I can use m equals 1 just as a rough upper bound and know that that 5th derivative of f at c must be less than 1, since this is just going to be, we computed it minus sine, minus sine of 1, the absolute value of that, and that has to be less than 1 because the biggest the sine function ever gets is 1. So when I use m equals 1, this quantity here from Taylor's theorem becomes 1 over 120 times 1, and 1 over 120 is less than 0.01, which is 1/100th. So here was our value for T4 of 1. This was our approximation using the fourth degree Taylor polynomial. If you just use a good calculator or computer, you could actually compute cosine of 1 as 0.54030, and you can see how close they are. They're actually much closer than within 0.01. 0.01 is just the maximum possible thing the error could be. The error will be something in general smaller than that. How big is the error? Well, here we have, if we look at 0.5417 and we subtract 0.5403, the actual error, cosine of 1 minus T4 of 1, is really approximately 0.0014 something, which is much less, it's about a seventh as big as 0.01. So Taylor's theorem did tell us a good upper bound on the error, but the actual error, as you would expect, is much smaller than that. Let's look at a similar example where f of x is the exponential function. How close is T4 of 1? Remember here T4 of x, the fourth degree Taylor polynomial for the exponential function, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. One can easily compute T4 of 1 and see it's 1 plus 1 plus this plus a half plus a sixth plus a 24th. That's easy to add together. You can probably do it in your head and you get 65/24, which you can compute as approximately 2.7083. In fact, it's exactly 2.70833333 with the 3's repeating, but we'll just use that as an approximation. And the question is, how close is that to f of 1, which is e to the first power, which is just the number e. So is this a good approximation for e? T4 of 1, that came from just a beautiful polynomial function with rational coefficients? Well, the error, how wrong this is, how different this is from e, can be bounded using Taylor's theorem. It says R4 of 1, the size of the error, is at most some number m. This is a different m from the previous problem. This And again, we have to divide by 4 plus 1 factorial, and we multiply by 1 minus 0. Remember, 1 is the x we're using, 0 is the a we're using, raised to the 5th power. So just like before, this number is 1, this number, the denominator is 120, but now we're going to use m equals 3. Why? Because f of x here is e to the x, f prime of x is e to the x, f double prime of x is e to the x, and that will always be true. And what does m have to be? M must be an upper bound on the 5th derivative of f at c, where c is between 0 and 1. Well, the 5th derivative of f will still be the exponential function e to the x. It gets biggest when the input is biggest. It's an increasing function. So this whole thing is at most the exponential function at the biggest value of c, which is 1. In other words, an upper bound m could be just the number e. Well, if we don't know exactly what e is, then how do you pick m? Well, m can be just any number that's bigger than e. And one thing you probably learned about e, and it's a relatively elementary approximation, is that e is certainly less than 3. So we can use m equals 3, and we know that will be an upper bound on this 5th derivative of the exponential function at any number between 0 and 1. So the error for, this should have been R4, the error for in the 4th degree Taylor polynomial at the value 1 is at most 3 over 120, which is 1/40th, which is in decimal 0.025. Now, if you use a calculator, you'll see that the actual value of e is approximately, that should be approximately 2.7183. And here you see that the computed value here, t4 of 1, from our 4th degree Taylor polynomial estimate was 2.7083. So e minus t4 of 1 was actually approximately this minus this. That's about 0.01. And Taylor's theorem said, okay, the error is definitely less than 0.025. And 0.01 certainly is less than that. In fact, it's less than half that, about 40% of that, give or take a bit, which is what is to be expected. The error should definitely be less than this maximum error that's guaranteed by Taylor's theorem.